So, dear Professor Corvus, thank you for the kind introduction. Dear Professor Schmidt, dear Professor Meyer, greetings to Canada. I hope you can see and hear me now. Dear colleagues, dear friends and family, imagine you were in preparation for a hiking trip in the wilderness, and part of this preparation would be choosing the optimal GPS navigation system. You'd not only want to use this navigation system for navigation purposes, but also for the estimation of the hiking lengths. Let's say there were two best navigation systems recommended to you, one with a better spatial resolution and the other one with a better temporal resolution. So you were not able to decide which system to take. So you decide to take both of them with you. So it might happen that while you were traveling and both systems were recording your positions, that on the first part of the trip, system A indicates a hiking length, which is closer to the actual hiking length. It furthermore might happen that on the second part of the trip, system B indicates a hiking length that is actually closer, or that is closer to the actual hiking length. So what is the difference here? Maybe besides some random effects in the measurement uncertainty, the main difference here is the shape of the path. So we see on the first part of the path, there's a rather straight path. And on the second part of the path, there's a more curvy path. And that simply explains this phenomenon here. Because if you imagine you would have a perfectly straight path and you would measure it with multiple samples, but with a low spatial resolution, which is related to the meaning of measurement uncertainty as we typically use it, then the measured lengths would tend to be longer than the actual lengths. However, if you would measure a path which is curvy and you would have too few samples, you would have an undersampling problem. So your temporal resolution would be too low here. And the measured path would tend to be shorter than the actual lengths. And this phenomenon, or this opposite effect, is overlaid in this example, which leads to this result. So which GPS navigation system performs better now? The answer is it finally only depends on which path you choose. And that brings me to my next slide, where I want to introduce the trilemma in measurement of non-stationary measurands. So if we just measure stationary measurands, which could be represented, for example, by a traveler which has a constant direction, which would lead to a straight path here, only the spatial resolution, which is here related to a dimensional measurement, would be critical for the overall measurement error. However, there is a second goal, and this is the goal, the reduction of the measurement effort. So we would tackle these two goals by first taking care that we meet the requirements with the spatial resolution, and then afterwards we would try to reduce the measurement effort as much as possible. However, when it comes to the measurement of non-stationary measurements, then a third goal pops up, and that is the increase of the temporal resolution, which also represents the measurement time or the measurement frequency. And we saw for the introductory example that this third goal now also directly critically affects the overall measurement error. And we will also see in the following that these three goals are kind of conflicting with each other, that we have a trade-off problem here. And I will use this trilemma in the following as basis for my modeling approach. I will structure my presentation in three parts. First, I want to give a brief overview of the state of the art. I will formulate the scope and the research question. Then comes the main part, where I will stepwise investigate and develop my modeling approach. And by that, I will also do some experimental applications. Finally, I want to close with a conclusion and an outlook. So to get an overview of the state of the art, I first want to classify different measurement signals. So we can name here, for example, static or quasi-static signals. And they can be described by the fact that a potential change of the measurement during the measurement has no critical effect on that measurement. it looks like this. So we have a static measurement signal and the measurement result. And for sure, this measurement result has an uncertainty, which comes through different disturbing influencing factors. But typically, we do not consider here a change of the measurement. This could be explained or represented by this example. We see the scale, which measures the weight. And while it measures the weight will probably not change. However, we also have the opposite situation, and there are the dynamic measurement signals. And if we look in literature, these dynamic measurement signals are related to dynamic measurements, which can be described by the fact that the change of the measurement has a strong feedback onto the measurement system, and also the change is kind of highly dynamic. However, the strong feedbacks leads to a situation that the measurement system itself gets in a dynamic state, which may lead to high measurement errors. Here we see an input signal and the output response of the measurement system, and we also see some big or huge overshoot errors. Exemplary measurements, for example, are the measurement of forces during car crash simulations, or the measurement of moments during the tensioning of screws. But there must be a third group. And this can be described by the fact that the change of the measurement during the measurement has also a critical effect on the measurement, but there's not that critical feedback onto the measurement system. And the measurement system does not get in a dynamic state. This could basically described by the critical ratio between change of the measurement and measurement time. So if we start the measurement, we would typically only have a measurement uncertainty related to a static signal. However, as the signal or the measurement is changing in between the measurement, at the end, we have an increased uncertainty, which comes to this measurement time. We do not have this critical feedback, which can be explained that we do not have a mechanical measurement principle here like we have here. For example, we're just measuring with optics, so the photons coming from the measurement object do not bring the measurement system in a dynamic state. However, when does this occur? So this typically or most likely applies for indirect and sequential measurements, because there we have a lot of single measurements which only provide a piece of information, which we cannot interpret it on its own. We can only interpret the overall result. So if we take the entirety of all signals, we can then, for example, reconstruct the desired measurement here. So at the end, we still got one measurement, one timestamp, and with a increased uncertainty, which is due to the expanded measurement time. So these type of measurement system combines a lot of aspects of complex measurements. We have a multitude of influencing factors, indirect measurement, and the impossibility of repeated measurements, because the measurement is changing. We cannot just say, let's repeat this measurement now. If we could control the measurement so that we could repeat it, then we would not have this problem at all. And what about, so what are exemplary measurement systems? I will name a few of them so that you get a variety. For example, computed tomography, or magnetic resonance imaging, or photogrammetry, or the GPS-based length measurement, which we saw in the introduction, or from a production technology domain, sequential multilateration, which is a calibration technique for machine tools, or simply a CMM diameter measurement. So for the last example, we typically don't have to deal with non-stationary measurements, but if we would, it could become critical quite fast. And this list is still far away from complete. However, what about the measurement uncertainty estimation for indirect and sequential measurements of non-stationary measurements? If we look into the common state of the art, let's say the typical standards here, like the International Vocabulary of Metrology or the Guide to the Expression of Uncertainty in Measurement, the GUM, we see that these documents do not address non-stationary measurements. And they also do not help, for example, they do not describe a method to create a reference for a non-stationary measurements. And that is a huge challenge, though. However, there are further documents. For example, the measurement uncertainty estimation based on simulation, which is described in the GUM Supplement 1 and Supplement 2. They are kind of generally applicable, but we do need a model then. And this is also a quite challenging task. So if we now look on the state of the art in research, so this is just an abstract here of some relevant publications and dissertations. The summary is that I didn't find a publication or a document which addresses this combination. So the combination of indirect and sequential measurements and non-stationary measurements. However, I still can draw some conclusions here. So it would theoretically be possible to use this simulation-based method. However, then we would require a specific model for this measurement system. And this is still a huge challenge. Furthermore, in situ model evaluation would be needed for every measurement to provide an uncertainty. And then lastly, if we would use the Monte Carlo simulation, for example, for this estimation, we would have to consider input signals, which open up a lot more of complexity, a much bigger parameter space here compared to considering only input values for stationary measurements. So to make it short, I can also not solve this issue in this presentation here. I can also not provide a general model which fits for all these different types of measurement system. I'm rather looking on that problem. I want to look on that problem from the other side. So I search for a model which helps to reduce the effect of non-stationary measurements. And that brings me back to my trilemma. So the research question I want to address is, how can an optimal setting within the trilemma be approximated when dimensional non-stationary measurements are measured using indirect and sequential measurement methods? And I want to start my investigation with the trade-off problem between the temporal and the spatial resolution on the example of a medical CT scanner. So CT scanners for medical use are very important for the diagnostic of anomalies inside the human body. A physician, for example, may use a CT image to decide whether a surgery has to be done or not. That's a very critical decision for a patient. However, this decision may be influenced by the CT image quality, which may be disturbed by non-stationary effects. For example, the movement of the patient, the respiration of the patient, or also the heartbeat of the patient. And we see we cannot just stop these non-stationary effects. So how does a CT scanner work? We have a spinning gantry, which is nicely visible with this on this picture here. And on this gantry, we have an X-ray source, which emits an X-ray beam, which is transmitted through the patient or the measurement object, and which is then measured with the X-ray detector. So the remaining intensity of this X-ray beam is detected. And it looks like that while the gantry is spinning, we measure the intensity distribution. And if we plot it over the angle of the gantry, we got the so-called sinogram. And the sinogram can then be used for the reconstruction, which is based on an inversion of this projection, which is called back projection. However, how does a typical measurement strategy look like? It would look like that the gantry would continuously spin. And while the gantry is spinning, we would continuously take in images. For example, with a constant angular increment of 10 degrees. So what if a critical non-stationary effect in the measurement would occur now during the measurements? And if we would just have a sequence of 3 images where the measurement would be stable, just for example, we can just say a reconstruction would not be possible. We have not enough information here. And that's a general problem. Also, if we would have a longer sequence, we just need a stable measurement for this reconstruction. So in the following, I want to discuss an alternative measurement strategy. And for that, I would ask you to ignore for a moment the spinning speed of the gantry. I will only focus on the sampling. So one could think that it would be good to increase the angular increment to increase the amount of information here. Let's say up to 120 degrees. Then we would have a homogeneous distribution of images in the full circle. However, if we would repeat this measurement, then we would have the same amount of information, for example, with 99 scans. So that is not ideal. If we would increase the angle, let's say by 0.5 degrees, we will see these perspectives spread up, but they still far away from homogeneous. So we could think that increase the angle just further. And if we do so, we come to a point where we meet a good approximation of the golden angle. And the golden angle is a very unique angle, which I want to explain in the following. However, we see that with this angle, we have kind of a homogeneous distribution of perspectives here. We see that we have a few gaps, but all these gaps have kind of the same width. And we also do not have a real clustering of samples. So what about the 3 images then? So 1, 2, 3. We see that now we have not that homogeneous distribution as we had for the 120 degree. But if we look on it, we see that this distribution provides much more information about our measurement object. So if our first sample would, or first image would be here, a second image from that position would not make sense because it only provides kind of redundant information. So the highest amount of new information could be achieved with a perspective here or there. And we see that we are quite close to this position. However, the next image then, the third image, should be there, there, or there. And we see that we are actually quite close to this position. So the next image then should be here. And if we go one image further, we see that we are still quite close to this position. However, now we could think, why not being perfect? We could just use 135 degree and then we would exactly match these positions. The point is we would not get any better than this then, because after the fourth image, we would run into redundancy. And that is not the case with the golden angle. Here we will always add new and valuable information, and this will go on forever. However, not when we just use an approximation. But we can say that when we use the golden angle, the rate of information or the acquired information per image or per sample is kind of maximized here when we look on the entirety of samples. And why is it so? So let's have a look on the mathematics. So the golden angle is derived or can be derived from the golden ratio. And this is a unique number. It is an irrational number, and it is stated that it is the most irrational numbers, the number of all numbers. And this is based on a simple mathematical proof which says that this is the hardest number to be approximated by a division of two natural numbers. And we would find this best approximation of these two natural numbers at the infinite end of the Fibonacci series. So if we divide 1 by this irrational number, we got the so-called golden mean, which is a continuous fraction. And if we multiply a unity by this golden mean, we can use this to sample through this unity in kind of an ideal way. Ideal means that the samples contain an optimal amount of information per sample, and that these samples are kind of homogeneously distributed in this unity. So in our example, we use the full circle as the unity, but we could use everything. It could be a fraction of the full circle, it could be a line, it could be a parameter range, whatever would be interesting to sample through. And we see this phenomenon also in nature. For example, sunflowers have learned by evolution to distribute their seeds in a way that each seeds kind of maximize the amount of collected sunlight. And the sunflower also uses the golden angle. However, do we find that method now in use for CT scanner? And if we see the state of the art, then we have to say not for the typical operation mode. The reason is the sampling time is not the bottleneck. The bottleneck here is the spinning speed. So it would not make sense to wait until to take a next sample until the gantry has been by the amount of the golden angle. However, there are still some applications. For example, if you think you want to localize a foreign object in the human body and you want to localize it quite fast, it would make sense to use this golden angle instead of using a 10-degree increment. And the positive side effect would be that the radiation dose for the patient is also lower because you have the highest amount of information per sample, which is much more efficient then. However, if we look on other measurement systems, we do find a lot of applications. For example, in industrial tomography. So the setup is a bit different here because we do not scan living beings, but object, we can scan the object. And that may lead to another ratio between spinning speed and sampling time. So there are special type of CT scanners where the sampling method does make sense. And furthermore, we see here some researchers which use just a typical industrial CT scanners, but they call it 4D computed tomography, which means that the time is the fourth dimension here, which they also measure. That means they measure continuously. For example, that's not good. For example, the evolution of a growing seed. And they state that with the golden ratio sampling, it is easier to find a better trade-off between temporal and spatial resolution. And if we look on, for example, OCT for corneal topography, which is a special measurement technology to measure the topology of the eye, there the researchers state that with the help of the golden angle, the need for a repeated measurement in case of abrupt disturbances, this need is reduced. And this abrupt disturbance could occur due to a sudden blink of the eye, which is quite probable, which could happen quite fast for this type of measurement. So it does make sense to increase this amount of information before that happens. And if we then also look on magnetic resonance imaging, we see a lot of publications and discussions where the advantage of golden angle-based sampling is discussed. So here it is stated that in recent years, the golden angle radial sampling has become a popular sampling trajectory for both research and clinical use. And this is, again, only for that reason that we want to increase the spatiotemporal resolution here. However, then I thought if it is a general approach, can we use it also for other measurement system or principles? So I thought, what about photogrammetry? Photogrammetry is also an indirect and sequential measurement method. And here we use 2D images for a 3D reconstruction. We not look through the image or through the object, we look on the surface. But the basic process is that we take several images, and on these images we find recognizable features, and on different images we find matches between these features, And with these features, which are here represented by the red dots, we can use triangulation to calculate the camera position. And if we know the camera position, we can then use triangulation for each pixel to reconstruct the scene or the 3D object. So I had to design an experiment, and I just said I will use the Herbert Opitz statue here. So Herbert Opitz is a former WZL director, but I had to bring this statue in a non-stationary state, so I just let it melt like ice cream, for example. However, then it would make sense to digitalize this object before it has gone. So the question would be how to distribute these camera positions on a surrounding sphere. And a typical approach would be just to use the crossing points of these geodesic lines here. I think we use this approach also in the shop floor for our scan box. However, then we would have a higher density of images at the poles and a lower one at the equator. And we again search for a kind of an even distribution here. But we have to say a perfect even distribution only exists for 4, 6, and 20 points, represented by 3 of the 5 Platonic solids. In all other cases, we can only approximate an even distribution of points. And the most popular method uses the spherical Fibonacci lattice, which is again based on the golden angle. However, we see when we look on the sequence here that we only have an even distribution of points at the end of the sequence and not during the sequence. So this is also not the right method. So I had to search for a better one. And here I can mention, or we can mention that using a golden mean approach, which is derived from the golden ratio, this is only applicable to one-dimensional problems. We can only sample through a one-dimensional unity. But luckily, there is a way to derive 2 golden means, and this could be done quite simple. So if we just change I-2 to I-3 here in this Fibonacci expression, then the Fibonacci series changes, and then it provides 2 characteristical quotients which represent the 2 golden means. And with these 2 golden means, we can then sample also through a 2-dimensional unity. And this could be, for example, this unit square. And we see that we have kind of an even distribution of points here. And if we compare it to a random point approach, we directly see the better performance here, because we do not have this clustering. We do not have these gaps. And furthermore, using this golden mean approach leads to a reproducible sampling method, which is also quite important for measurements, because we want to also reproduce a measurement strategy to make results comparable, for example. So based on these 2 golden means, I designed a new measurement strategy. And on the left side, we see, I called it the advanced state-of-the-art strategy, which is based on the Fibonacci lattice. And on the right side, a new strategy based on the golden mean sampling approach. And we directly see the difference here. So the right side provides an even distribution, or kind of even distribution, in all points in time, which is not the case for the left side. However, at the end of the sequence, we have a kind of similar even distribution here. And in case you haven't seen, this model here is actually melting during the sampling. So that is in fact the same melting effect which I used for this experiment. So I designed the overall experiment pipeline like this, that I have an initial static model, which is in fact a real 3D scan, in case you're wondering why is the eyes looking so weird. However, then I tested the pipeline, which I built using Blender for the whole simulation part. And I exported these images to Meshroom, which is also an open source software for photogrammetry reconstruction. And we see that the reconstruction of the static model worked quite well, and the results were similar for both approaches here. However, then I had the non-stationary model, and here again you see this melting effect. And to reconstruct this model, I had to add static references or static features in the background. The reason is otherwise the structure from motion part, which calculates the camera position, would not find any static feature for this calculation. But this is even still more even more realistic, because we would also have static features in the background for a real scenario. However, then I got some results. So first, I again tested this reconstruction for the static model, and we see that with the Fibonacci lattice approach and the new strategy, the results are again quite comparable here. Furthermore, then I reconstructed the non-stationary model, and we see that the result is not beautiful anymore. We have a lot of artifacts here which are no surprise, because during the measurements, the whole surface or the phase region is melting. But if I take the same images of this measurement and I just reduce the number of images, I get another result. And for the upper one, we see that here the upper region is okay, but at the lower region, we can not do a reconstruction at all. And that is no surprise, because we have only pictures in the upper part of the sphere. However, that's not the case for the lower reconstruction, because there we have also an even distribution. And we can say that this result is the best of these four. And the reason is, by reducing the number of samples here, we kind of increase the temporal resolution, or we decrease the measurement time, while also decreasing the spatial resolution. But we kind of find a trade-off somewhere. And that brings me to my next slide, where I want to do the modeling here. So let's say we want to measure a non-stationary measurand for a specific condition or a specific point in time. Then we can say that for this time, let's say the start point of the measurement has not changed at all. And I call it the measurand congruence. But if we move forward in time, the measurand will change. We do not know how it will change. So we do not know how this curve will look, if it looks like this or this, whatever. This is unknown. In the following, I will just use a linear degrees of measurand congruence for simplification. However, we can then also add a second curve here, which I call the information coverage. And this curve describes the amount of information acquired about our measurement object. If we think of, for example, a reconstruction method where I use a constant angular increment, and the image which I make has a constant overlap region with redundant information and a constant region with new information of our object, then we would get a linear increase of information per image, which would lead to this linear curve. Furthermore, if we would use a constant angular increment, which would run in repetitions after some samples, we would never reach 100%, whatever this 100% is. We would reach some, or we would end at some other value here. And if we multiply these two curves, we got a third curve, which I call the measurement quality here. And I also defined the meaning. So this measurement quality here is the level of relevance of the acquired information to a specific state of the measurand. And we see we have a peak point here. So this peak point here describes the highest, or the trade-off for this type of measurement, the trade-off between temporal and spatial resolution. And the specific state here at this peak point would describe the state of the measurand for this time span here. However, if we now would use a golden mean sampling approach, this would change the shape of this information coverage curve, because we saw that the first sample contained kind of a maximized amount of information, and as we use an irrational number for angular increment, we will always get a new perspective. So we will always add a new piece of information, which will become smaller and smaller and smaller. So it has to be a shape like this. And this will also affect the measurement quality. Here we see we have a higher peak point now. And if this represents a specific number of samples, then a reduction of samples could, for example, lead us to the peak point here, which would describe the trade-off or the optimal trade-off between temporal and spatial resolution. And if we just would say that the measurement would not change at all, so we would have a stationary measurement, then this coverage or this measuring congruence curve would just be straight on 100%. And we see that in that moment, the temporal resolution is not critical anymore. However, we can now bring it on the trilemma picture, because this already is a partial answer to my research question. And we can bring it on this side here. So this model here explains how to find a trade-off, or a kind of optimal trade-off between temporal resolution and spatial resolution. And we just affect this by the measurement strategy. So this will not affect, for example, the cost domain. The cost domain is only in that dimension here. But if we are in this plane here, this will only be affected by the measurement strategy. And the measurement strategy will at least change, or will change the shape of the curve. So if we say we have used the golden mean approach, which is kind of the optimal sampling method here, and we would just take the same images, but we would just use them in a different order, this curve could also get this shape, which would be far from ideal. So we can say that the measurement strategy affects this curve shape. So, but there are still some blank spots on this picture, and I want to address them in the following. The question is, how do the measurement effort affects the other two goals? And the simplest form of a measurement effort increase could be represented by a system multiplication, which is a common practice though. Here we have a single source CT, and there is a newer type, a dual source CT. We have a single camera approach for photogrammetry, or we can use multiple cameras at the same time. We can use a single laser tracker for calibration purposes, or we can directly use multiple laser tracers. However, all these measures improve the spatio-temporal resolution. So what happens exactly? The question I want to address is, how does the system multiplication affect the overall temporal resolution or sampling rate? So it is kind of obvious that the acquisition rate will increase if I use multiple cameras, but what happens with the limiting factor like the sampling rate? And if we look at this picture, we can think that, or we can say that in theory, each camera could be triggered separately. It's a technical problem, but that would lead to a linear increase also of the overall sampling rate of the system. So we have a proportional relationship here. And the next question is that how does the system multiplication affect the overall spatial resolution? And if we take an exemplary 4x4 pixel range of the camera, which is, for example, pointed on a texture, then a multiplication would also affect the resolution. As we assume that if we point multiple cameras on the, let's say, same object, it is very unlikely that the resolution increments are perfectly aligned. They will not. And we can easily also calculate the probability for a resolution increment in the range of 1 pixel. So if we take a normal distribution here and we assume that the standard deviation of this alignment error, let's say, which is a valid approach or which is valid, then the overall probability for an increment in a pixel area would be n, which would mean that also the resolution is increased linearly. And we see also when we multiply here the cameras up to 100, we see that the resolution definitely kind of increases. Let's bring that also onto the trilemma picture. So if we give up this goal, the reduction of the measurement effort, for example, by a multiplication of the system, this will lead to either a linear increase to the temporal resolution or to the temporal resolution or to the spatial resolution. At least this is the limit. We cannot get better than this. And furthermore, this also affects the information coverage curve, but in another way. It will kind of compress this curve to the left. Yeah, we see it here. It will be compressed to the left, and by that, also the peak point of the measurement quality will be increased. So that is my modeling approach. It is still not perfect yet and probably not complete, but maybe it will help somebody in future to find an optimal setting for a measurement system, or an optimal design for a measurement system when it comes to the measurement of non-stationary measurands. However, this still, so I will draw my conclusions now. The initial or the research question was, how can an optimal setting within the trilemma be approximated when dimensional non-stationary measurements are measured using indirect and sequential measurement methods? To answer this question, a modeling approach was developed, which provide helpful information about the trade-off relations between all three conflicting trilemma goals. And in case the sampling time is the limiting factor, then a golden mean approach may help to find a nearly optimal sampling order. And if we have this optimal sampling order, this will allow to find an optimal trade-off or nearly optimal trade-off between temporal and spatial resolution in the post-processing step. So we could never know that before, we can only find it afterwards. And furthermore, a golden mean sampling approach was tested as a measurement strategy for a photogrammetry-based reconstruction of a non-stationary 3D model. And the new method showed significantly better performance here. So this will, or in this domain, there is still a lot of research potential, but I will name a few follow-up research questions which I think are important for my approach here. So I tested this approach for a dimensional measurement and also for the reconstruction based on photogrammetry. So the question arises, is this approach generally applicable also for other measurements and also other measurement principles? Furthermore, I just compared the reconstruction result with the initial model to analyze whether the measurement quality increased or it was better or not. However, the question is, maybe we can find a method which helps us to find this peak, maybe automatically, because we cannot always just compare the result by the real result. Yes. So that is an important question. And furthermore, I haven't talked about on-the-fly measurements. So on-the-fly measurements can be described by a measurement mode that the measurement is done continuously, and the measurement object or the measurement system is moved around the measurement object, or the measurement object is moved while we're measuring continuously. So this will offer a great potential for a further increase of the acquisition rate of information. Think of, I would not take single images of the object, but I would rather make a video and move the camera around the object. However, then a follow-up question would be, can we find an optimal trajectory for this movement? And maybe this optimal trajectory can also be found with the golden mean approach. Maybe it will a bit look like this. And maybe a future 3D imaging machine will a bit look like the machine with which Jodie Foster traveled through time and space in the film Contact. But this is still written in the stars. Thank you.